Hello everyone. In this lecture, you are going to learn how to represent positive and negative numbers, that is called signed number representation, and then Radix complement number system and Radix complement arithmetic. I have started this video lecture series, and on number system itself, I have previous 4 videos. And there I have told you that there are so many different number systems are there: binary, octal, decimal, hexadecimal. And I have also shown you how to do arithmetic like addition and subtraction with those numbers. But that time I only considered the positive numbers. But you know that we also have to consider the negative numbers. So today I'm going to show you how to represent the negative numbers for the computer. Usually when we write on a paper by hand, we usually use this plus and minus sign for positive and negative numbers. So here it is showing n is a number which can be positive or negative, any one of them, and the rest of the is given in positional notation, which you have shown before, and the digits in front of the point, which is called the radix point, is the integer part of the number, and the digits after the radix point is called the fractional part of the number, which you have learned before, and you have also learned how to convert one base to another base. So, so now we're going to see the signed number representation. So for that, the sign bit is shown here specifically. There needs to be one extra sign bit, and usually this bit is 0 for positive number and is equal to radix minus 1. So if we are considering binary number system, radix is 2. So 2 minus 1 is 1. So s will be 1 for a negative number, and rest of the magnitude part remains the same. But if we are considering a decimal number, so in a decimal number, the base of the number, so for that, the positive numbers is s is 0, but for negative numbers, as the radix is 10, it will be 10 minus 1, 9. So minus 15 representation in decimal number with sign and magnitude will be 9, 15. And here it is written as a subscript 10. 10 is the decimal number representation, and S and M stands for sign magnitude number representation system. So this is one way of representing the negative numbers by use of an extra digit. For binary, it is 0 for positive and 1 for negative. And decimal number system, it will be 0 for positive and 9 for negative number. And this is what is called signed magnitude number representation system. But there are other methods are there. So here we are going to see that other method which is used for a computer and which is called complementary number system. You must have heard of 2's complement number. So we are going to see that 2's complement number, or in general Radix complement. 2's complement number system is used for binary numbers, and this radix means in general for decimal it will be 10's complement. For hexadecimal we'll call it as 16's complement number to represent both positive number. So this is the complementary number system you are learning here. So in general you can call it as a radix complement or R's complement. R stands for the radix or the base of the system, and it is represented, a complement of the number is represented within the square bracket. R is the radix, equal R to the power n minus this number in that number system, and where n is the number of digit in n, in the number. Okay, so depending on how many digits we are using to represent the number, that width of the number n, it can represent only few positive numbers and few negative numbers. So here it is saying if n is the number of digit you are using to represent the number, you can represent at the most r to the power n minus 1 minus 1 for as a positive numbers. I will give an example. If you are using 4 bits to represent a number in a binary number system, then you can represent 2 to the power 3 minus 1, that means 7. So 0 to 7 positive number you can represent with bits, and for negative number you can represent up to 2 to the power 3, 8. That means minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8. So you can represent one more negative numbers than positive number with n bits of representation. Okay, so for number system you can use a 2's complement number system, and in 2's complement number system with n bits you can represent r 2 to the power n minus 1 minus 1 positive number, and 2 to the power n minus 1 negative numbers. There is, you also heard that 1's complement number. So this is called the diminished radix complement or r minus 1's complement. So if r is 2 or binary number, so 1's complement will be r to the power n minus the number minus 1. That will be the complement of a number. So let's see it with some numbers itself. So complement number. So this is a binary number which is given. Can you tell me what is this number? How to know its decimal equivalent? So this is 0, 1, 2, 3, 1 in this location has the value of 2 to the power 5 is 32. 32 plus here it is 9, right? And so 32 plus 9 is, this number is 41. So the complement of this number is given with inside the square bracket of 2 is, because here how many digits are there? 1, 2, 3, 4, 5, 6 digits are there. So the complement of the number is 2 to the power 6 minus the number. And what is 2 is 64. 64 minus 41. 23. Let's see. 0, 1, 2, 3, 4. Here it is 16. 16 plus 7. 23. So the complement of 41 is 23 in 6 bits of representation. You always have to mention how many bits of representation you are considering. Okay, so depending on that, these values will be changing. So it is always true that the number added with its complement, here digits, right? 6 digits. 6 bits here, 6 bits. Here you are getting a result which is 7 bits. But if you just ignore this, the rest of the 6 bits is all zeros. So basically what you are getting is the number added with its complement is all 0 with n bits of representation. So that's why this complement number representation can be considered as the negative of the number. Whatever the number was there, the negative of that number is this. That's why when you are adding the number with its complement, you are getting the result as 0. And here it is showing if you take the complement of the complement, you will get the original number back. Okay. So that's why this two complement number system is used in a computer because it represents the negative of the number. Now here it is showing 2's complement of this number. You know this number is 10, positive 10 for n equal to 6. So what will be the complement of the number? Complement of the number will be 2 to the power 6 minus this is this one. Okay, it's a big number. What is this number? You tell me, write me in the comment section. Okay, now 10's complement number, because the subscript is 10, the number is 10 in a decimal number system. Suppose this is a number in decimal number system. What is its complement? So we are using 5 digit to represent the number. So the complement will be calculating the power, here it is 10 to the power 5. That's why 5 zeros are there, minus the number. So this is the complement. 27,908 is the complement of 72,092. Can you tell me what is the complement of decimal number 3? Easy. 3 is a 1 digit we are using, so it will be 10 to the power 1 minus 3 is 7. Okay. What is the complement of 30? It will be 70 because 30 has 2 digits. So we'll be using 10 minus 30 is 70. It is like that. So Radix complement number system, we may want to find the complement of the number given a number. In the previous slide, we saw that you take 2 to the power minus the number, but there is another way the complement of the number, and that is given here. First, replace each digit ak of the number by r minus 1 minus ak, and then add 1 to the resultant. So if it is a binary number system, you will be minusing each from 1, because it will be 2, 2 minus 1 is 1. You will be minusing each bit from 1, and at the end you will be adding a 1. So this is basically 1's complement plus 1. For binary numbers r equal to 2, complement each digit and add 1 to the result. So here it is showing that this big number, and so you are complementing each digit. You do it from left hand side or right hand side, doesn't matter, because you are considering each bit separately. So you are complementing them, and later on you are adding 1. So this is becoming the complement number. Find 10's complement of this number. This is a 5-digit representation. Here also, we are not going to do the minus technique, take 5 minus the number. We are just going to complement each digit. So here we will be complementing 10 minus 1 from, so 9, from 9 will be 9 minus 0 is 9, 9 minus 6 is 3, 9 minus 9 is 0, 9 minus 0 is 9, 9 minus 4 is 5. So 59039, and then you are adding 1. So this is the complement of this decimal number. Hope you are understanding this concept, and if you need more time, please pause the video and look again. So 2's complement number, positive numbers, the positional notation of the number, right? And you know that how many positive numbers you can represent depends on the width of the data. That means how many bits you are using. And for positive number, the most significant bit of the number is always 0. So 0 to n minus 2, right? That means n minus 1. You can have this bit is always 0. 0 to n minus 1 is the total width of the number, and out of that this most significant bit is always 0, and rest of the bits will be representing the positive number. And the number you can represent, as I said before, will range from 0 to 2 to the power n minus 1 minus 1. And for negative number, this bit minus 1 will 1, and this is the rest of the digit, and it can represent minus 1 to 2 to the power minus 1. So negative 1 number, the maximum value or the minimum value is 1 more than the maximum positive value. Example of 2's complement number system. So n is this number, you have to represent with 8 bits. In the original number there are 7 bits, right? So you will be considering it is a 0, you add a 0 to make it 8 bits, and this, then if the most significant bit is 0, it is a positive number, and now you want to get the complement of that number, so it will be a number. And so you can see that you already know how to take the complement. You complement each bit, right? Each bit of the number, each bit, this 1 becomes 0, 1, 1, 0, 0, 1, 0, and then 1. So it will be turn out to be this number. And here you can see that the most significant bit is becoming 1. Took the complement of a positive number and it became a negative number. Now if you add the positive number with the negative number, you will get a 0. So what is the 2's complement number, 2's complement representation of the decimal number 18, negative 18. So you know positive 18 is this in 2's complement. You are converting decimal to binary first for 18, and then you are complement the answer. You can solve it yourself to verify it. Now, what is the decimal representation of this number? If it is a 2's complement number, the initial one is telling that this is a negative number right then, okay? Other things you do not know yet, but this one, this is the negative number. So it will be a negative decimal number. So to know the number, you take the complement of this negative number. You get this number, minus 24. So complement of the complement, you are going back to the original number. Now we are going to see Radix complement arithmetic and why it is good. So in a digital computer, all addition, subtraction, and with a digital logic hardware. But Radix complement number system, you can do the subtraction also with the same adder hardware. So it is saying Radix complement number system are used to convert subtraction to addition, which is the hardware requirement. Only adders are needed. Like you have to do A minus B, so you can write it A plus minus B, and this minus B is the complement. If you take the complement of B, you get a minus B, and here it is still adding a positive number with a negative number, and you are using a adder hardware this time, and that's why in a computer 2's complement number system is used to do all addition and subtraction same way. And the range of the number it can represent depends on n number of bits. So the number you can represent ranges from minus 2 to the power n minus 1 to plus 2 to the power n minus 1. So 2 to the power n minus 1 minus 1 is this number, right? Some positive number it can represent is the most significant bit 0 and all other bits are 1. And for this number, negative number, the most significant bit is 1 and all others are 0. That is the range of numbers. It can be represented with n bits of 2's complement number system. So when you are doing arithmetic, you have to pay attention whether the result falls within this range that the number system can represent. If the result of an operation falls outside the range, we call it as an overflow. It is called overflow condition is said to occur and the result is not valid. That means if you consider still n bits of result, it's a wrong result. So the remedy is to increase the data width. So we'll be considering these three cases to see when the overflow is occurring or for overflow detection. Let's consider we have two numbers B and C, and all these cases we'll be considering both B and C are positive numbers. Now first case is when adding two positive numbers. Here in the first case overflow may occur, and in case we are subtracting a number from another number. In this case the overflow will not happen because the result will become smaller. In this case when you are adding two negative numbers, then also overflow may occur. So first case and third case overflow will occur, second case overflow will not occur, and we are considering both B and C to be positive initially. So case 1 we are doing A equal to B plus C. So if A, the result is greater than 2 to the power n minus 1 minus 1 is overflow, because we know that maximum positive number can be represented is 2 to the power n minus 1 minus 1. So the result cannot be more than that. So here you are using, example is 7 plus 4. In decimal it is written, and you have to add them. And it is said that use 5 bits of complement number system representation. 5 bits. So here these numbers are very small. So overflow shouldn't occur, right? 7, 10 is equivalent to this binary. And in 5 bits of representation, this 0 you are adding for a positive number. And 4 is represented like this. And 5 bits representation, you are adding this extra 0. And when you are adding them, you are getting this result. Okay, and this is positive 1011. So 11. This is it. This is number 11. And here no overflow. Basically, when you are adding to positive number, this most significant bit, which tells you right away whether it is a positive and negative number, will tell you that overflow has occurred or not. You added to positive number and you are getting a result as positive, so no overflow has occurred. So 5 bits of representation is okay for in this case. But in this example, 9 plus 8 in decimal it is given. So 9's representation in binary number, binary and 2's complement number system is a positive number. 8 is also positive. When you are adding them, you are getting this result. 5 bits of representation, right? And in the most significant bit, you are getting a 1, which tells you that it is a negative number. But that is not possible because you are adding to positive number. How can it number? So in this case, overflow has occurred and this is a wrong result. That means you have to increase the, instead of 5 bits representation, you have to use 6 bits of representation. Now case 2 is A equal to B minus C. I know that overflow cannot occur. So here we'll be considering both B and C to be positive. And because we have to minus it, we'll be taking the composite to make it a negative number. And then we are going to do simple addition. Okay. So here overflow will not occur. So no overflow in this case. So here it is giving an example 14 minus 9 in decimal. So you represent them with binary and then you, because it is a 5 bits of representation, you are adding this 0 in front and it is a positive number also. And 9 and you have taken the complement of it, no? So that minus 9 became this number. And you are adding them now and you got this result within the 5 bits and this is a positive. You are subtracting a small number for a big from a big number and you got a positive result. So here the result is okay, no overflow has occurred. Now, if you subtract a big number from a small number, like this in this example, you are subtracting 14 from 9, then also it is okay. You subtract it this because it belongs to case 2, so it is okay. No overflow has occurred here. Now case 3 is A equal to B minus C, and in also overflow can occur. If it is outside the range of the number, it can represent. You know that the maximum negative number, it it is from -1 -2 to the power n. It happens that range. And in this case, a overflow can occur if the sign bit is 0, right? You are two negative numbers you are adding, the result should be negative. But if you get them as 0, then you know that overflow has occurred. So like this, -7, -8, using 5 bits of 2's complement, you do it. And here you are getting the result. The sign bit is still negative, so no overflow. But in the second case, when you are doing -12, which will be -17, right? In -17, you cannot represent in 5 bits. So when you are doing it, you can see the result is this 0. The sign bit position has a 0. So you know that an overflow has occurred in this case. Please pause the video and you yourself know how to represent decimal to binary and how to take complement to complement, and you do the math and check for the sign bit values. Now see another example. 25, A is 25, B is -46, and using 8 bits of 2's complement. 8 bits is a big number to represent these small numbers. Overflow will occur here also. A 2510 is this is the 2's complement representation, and -A will be this, and B is this is the representation. So you do all of them, A plus B, you are getting minus A minus B, you are getting +71. There won't be any problem because you have taken a big data with 8 bits of representation. And B minus A also no problem. -A minus B +21, no problem. So you can summarize the whole thing, how to detect overflow has occurred or not. So let's assume B and C are positive number. So first case, if the sign bit is 0 and carry we are not, means whatever outside the range of digit, that is the carry. So sign bit is 0, two positive number you are adding, you got a sign bit 0. Overflow occurred? No. But if the showing that it has result is negative, overflow occurred. And B minus C, no overflow. It is not possible. -B minus C overflow can occur. Two negative numbers, the sign bit 1, but if it is 0, then overflow has occurred. Okay, this is given in a tabular way how to detect overflow. Now we see when numbers are represented using 2's complement number system, addition add to subtraction add 2's complement of the subtrahend to the minuend, and carry bit is discarded and overflow is detected as above. Radix complement arithmetic can be used for any radix. Here I have shown both binary radix and decimal radix complement, and it can be any radix point, octal, hexadecimal, or any other numbers.